Hello everyone, my name is Amanpreet Singh Chahal. This is my project presentation for class EEE 236, that is semiconductor physics. And today I am going to talk about silicon carbide logic circuits. So let's start with the structure of silicon carbide. As you can see in figure 1, the central atom is consists of carbon and the remaining 4 are silicon atoms. Now let's move to the figure 2, which shows three isotopes of silicon carbide, namely 3C, 4H and 6H, where number 3, 4 and 6 represents particular stacking sequence and H refers to the hexagonal crystalline structure and C is cubic symmetry. Cubic symmetry. As we all know, in today's world we use silicon for chip design, but what makes us to move from silicon to silicon carbide? So let's compare silicon carbide advantages over silicon. Band gap. In silicon, high temperatures can kick electrons into the conduction band, causing fault current to flow and fooling our logic operations, all due to heat. But whereas in silicon carbide, band gap is 3.3 electron volt, which is much wider, and that heat doesn't cause much conduction. High thermal conductivity. This property allows high current to flow at high temperature. High critical electric field. And this property allows high voltage to flow at high temperature. And now high breakdown voltage. As you can see in silicon it's 0.25, whereas in silicon carbide it's 2.5, so it's almost 10 times of silicon. Chemical and mechanical inertness. One can say silicon carbide is physically stable up to 600 degrees Celsius. High switching speed with low capacitance. As you can see in figure 1, silicon carbide turn-on losses during switching are very low as compared to silicon. And similarly, in figure 2, turn-off losses for silicon are least. The size of a transistor is one of the most important factor, and in the diagram we can see that we need only 90 micrometer of silicon carbide to isolate 10,000 volts, whereas we need 1000 micrometer of silicon, which is almost 10 times of silicon carbide. So those were some of the advantages of silicon carbide over silicon, and now let's talk about some of the disadvantages. Present, if you go to market to buy a MOSFET, then silicon MOSFET will cost $1, whereas silicon carbide MOSFET will cost you $15. Which one of these will you prefer? Obviously, silicon MOSFET. So you can imagine how much you have to spend to buy a chip consists of thousands of transistors. This is all due to wafer cost, processing and device design cost, and system integration cost. At present, many of the organizations are working to develop silicon carbide logic design to improve the speed, time, and area of the chip. And few are listed below that has major contribution in this area. Philip and his team is working at NASA Glenn Research Center and has developed silicon carbide ICs that function at 500 degrees Celsius temperature for thousands of hours, which is a huge achievement. Their first chip had only 10 transistors and now they are working on a chip which has more than 300 transistors. Intel. Intel has also stepped up and invested $1 million for the research. Their base. Scientists at Case Western Reserve University has pushed heat-resistant integrated circuits to a record 550 degrees Celsius, a notch hotter than the NASA scientists. On 21st November 2012, computers today use CMOS logic, which depends on transistors that contain a thin silver insulators inside them. But insulators for similarly structured silicon carbide transistors doesn't work well at extreme temperatures. So here scientists have shifted to JFET from MOSFET. JFET stands for junction field effect transistors. In this slide, let's discuss about the applications that need silicon carbide logic circuits. We need better sensors placed closer to the inside of the engine for fuel mixture that would allow the engine to run lean and smooth, lowering emission and saving oil. Secondly, Defense Advanced Research Projects Agency has funded the research at Case Western University and wants to use this technology on missiles to collect sensor information during explosions. Chip won't survive, but they think that information is valuable. Transmission lines and equipments, we need silicon carbide chips to work accurately at extreme temperatures, which is not possible with silicon-based chips. Important application of silicon carbide-based chips is to get sensor information from high temperature environments such as inside a jet engine or in a deep oil well. This could improve efficiency and save millions of dollars. Not to mention provide capabilities for space mission to extreme locations like Venus. To say that the application of silicon carbide logic circuits is not limited to just the above applications. If you have any suggestions or doubts, please comment below.